So let me talk today about the usefulness of quantum. So the talks that we had this morning, a couple of them were very technical, and what I want to do in this talk is I actually want to bring things back and try to set sort of a big picture approach to quantum, to address the questions of why we're actually working on quantum computing, and to talk in sort of general terms about what the value of quantum computing is and how we can think about it relative to superconducting, or supercomputing systems. Sorry, not superconducting. So just about 10 years ago, in October of 2012, I was actually at a conference in Taipei, and I gave a talk titled Quantum Computing's Classical Problem, Classical Computing's Quantum Problem. So now is actually a pretty good time to come back and revisit this general topic, I thought. And in this, I kind of addressed the issue of the relative success of quantum and classical systems and how that influences, how the incredible success of classical systems influences what quantum systems need to do. Now, that was 10 years ago, just right about the Keio supercomputer era, for which, of course, Riken and Kobe are well known. And now we are in the Fugaco era. So if we talk about the Fugaco supercomputer itself for just a minute, each CPU chip in the Fugaco has 8.7 billion transistors, almost 9 times 10 to the 9 transistors per CPU chip. And this is fabricated in a technology known as FinFET. Now, Fugaco only uses one chip per CPU node, or one chip per node. Some other supercomputers use more. But there are 158,976 nodes in this machine, right? The clock speed for the processors is 2.2 gigahertz. So that's 10 times 10 to the 9th power there. And let's assume, just for the sake of argument, that 10% of the transistors are switching in any individual, in any given clock cycle. A lot of computations, sort of these high-end computations, the supercomputing folks are accustomed to, take like a month to execute. So let's pick a month as sort of our number to work with here. A month is about 2.5 million seconds. So that means if you multiply all of these things together, that in 1 month, Fugaco can execute about 10 to the 30 logic gates. That is a lot of computation. So then the question becomes, under what circumstances then does quantum computing begin to bring us computational benefits that these classical supercomputers with these enormous computational capabilities can't actually achieve? So let's take a look at that. One of the problems with this, of course, is that I mentioned that these transistors are 7 nanometer transistors. In the figure here on the right, you'll see me leaning on a cube that we 3D printed that represents the crystalline structure of silicon. And that cube that I'm leaning on there represents about 1 cubic nanometer of silicon. So we are at the level already with these classical supercomputing systems and classical VLSI fabrication techniques, where we're dealing with transistor sizes that are already measured in terms of tens of atoms from one side of a given wire or one portion of the transistor to another portion of the transistor. Excuse me. So these are already just tremendously small devices, and we don't know how to build and use systems where individual transistors are smaller than the size of an atom. And so we're going to have to deal with that issue as we face it here. Moreover, thermodynamics is actually a big deal. These systems consume a tremendous amount of power, globally gigawatts worth of power around the world. So let me tell you a little bit about some of the recent advances in quantum computing, some of these recent successes First, in the context of what we call NISQ systems, the noisy intermediate scale quantum systems, which is a term you may have heard this morning. On the left, the two figures on the left, the lower left is a logical or an abstract representation of the layout of one of Google's quantum computers. And the figure above it is a context figure for a particular computation they ran on top of their system, in which they claim to have achieved what they call quantum supremacy, in which a quantum computer calculates something that a classical computer can't. Now, in this particular case, the problem that Google has actually gone and solved is they have done sampling from a distribution of random numbers, from a probability distribution, and then been able to turn around and characterize that random distribution. And so the assertion at the time was that in 200 seconds, they did a computation that would have taken classical computation 10,000 years. Now, people have since taken Google to task somewhat for that kind of naive characterization of the classical problem, and claim that the problem can actually be solved classically also much faster, but it gives you kind of an idea of where we are. The middle and right-hand part of the diagram here is from a recent paper out of Caltech, in which they have used a quantum computer in a machine learning problem. And in that machine learning problem, what they're doing is they're actually training the system and executing the training operations on top of the quantum computer. And in this case, they are looking for a particular high probability amplitude that represents one of the characteristics of a particular set of data in this case. So it's an ordinary machine learning program with the training phase and then the execution phase. And the claim is that the quantum execution of this training phase can be exponentially faster than a classical computer. So that's on the what we call the NISQ side. But as we heard this morning, there's ultimately the need to build fault-tolerant quantum computers, which handle error correction effectively. And here are a couple of experiments from some groups actually working on this. The set on the left there is a set of experiments representing error correction on superconducting systems built out of superconducting qubits of the type that Professor Nakamura talked about this morning. And then on the right is a representation of an experiment done by the group at the startup company called IonQ, in conjunction with the groups at Maryland and Duke universities, where their technology was born. And so these papers demonstrate that we are now standing right at the threshold where quantum error correction is starting to become effective for quantum computers. Now, why is that an issue? Well, in ordinary classical systems, we're used to executing a lot of error correction, but you execute error encoding essentially perfectly, put the data through a noisy channel, and then decode essentially perfectly. But in quantum systems, both the encoding and the decoding and the syndrome extraction process are inherently noisy processes themselves. And so the question becomes, when you're executing these circuits, are you inserting more errors into the state than you're extracting from it? And if you get to the point where you're actually making a net improvement in the error rate, that's what we call the threshold state, the threshold level. And we're sitting right about that level now. So over the course of the next couple of years, we'll see experiments going from, yeah, maybe that's error correction, to yes, this stuff really works and it works very well. So that brings us to the question. Now, this is a page taken from a manga that's, at this point, almost 20 years old, I think, a manga called Eden. And in the manga here, they have a supercomputer, an artificial intelligence that's actually a quantum computer. And so the legend here says, computer ga hitsuyou ni naru. So a quantum computer becomes necessary. So our question then is, when does a quantum computer become necessary for what we're doing here? Let me frame this for a few minutes in terms of the UN's Sustainable Development Goals, which is an issue that's been on our own minds lately. So this is what kinds of things quantum computers might actually do that might make the world a better place in sort of a broad sense. But we can kind of imagine two broad ways in which quantum computation can help with this. The first, of course, is computational products, meaning the outputs of the computation. We can use quantum computers to solve SDG-relevant computational problems. Second possibility is that we can potentially reduce the environmental impact of information and communication technologies by reducing the energy to solution for big computations of the kind that we've already been talking about a little bit. There are a couple of other possible advantages here in sort of the global societal sense that I want to mention just briefly. These are a little bit more controversial, perhaps, or a little bit harder to sort of quantitatively analyze whether or not we're actually getting particular benefits out of it. But the first is perhaps that quantum computation, quantum technology in general, can enhance our ability to execute computation and communication in a secure and private fashion, and that can lead to benefits in terms of human rights. Second, of course, is that just out and out, the computers, the quantum computers themselves represent scientific advances, and they also enable other scientific advances. Besides just solving problems for businesses or whatnot, they help us to actually solve scientific problems. And so in that sense, it helps us to advance society forward. But there's still a long ways to go before we get to the point where all of these things are sort of day-to-day kinds of outcomes of quantum computation. So let me give you, just for those who are not familiar with quantum computing, let me list 7 concepts here. We're not going to have time to go into all of them in detail, but if you'll put these 7 ideas in your head and you'll investigate these ideas, they'll help you to understand how it is that quantum computers actually work and how they go about solving problems. Now, the first is that quantum computers can handle data in superposition states. These superposition states are literally like having waves that create a superposition pattern, and you can have an amplitude for them and a phase for them. And this allows us to execute on complex states of our data rather than just ordinary classical zeros and ones at a time. Now, what the computational phenomenon, or the phenomenon we're actually using to compute with, is in fact interference, like interference of waves. I'll show you a little bit more about that in a second. And these two together, the superposition plus the interference, they get us what we call entanglement, quantum states that represent, that are non-classical in some sense and cannot be represented using ordinary classical probabilities. Now, a couple of the other concepts you're going to need: at the end of a computation, we measure the results of the computation. And these operations themselves have to be what are known mathematically as unitary or reversible computation. But of course, the big problems are, number one, decoherence. The systems don't work very well. They're subject to an awful lot of noise from the environment, and so that's a big problem. And number two, the no cloning theorem tells us some limitations on some of our computational capabilities. Now, if you're interested in learning more about this, if you're a beginner in this area, you can take our online course known as titled Understanding Quantum Computers, which is available through an online learning platform known as FutureLearn. And at the moment, this course is free. It'll probably take you on the order of about 20 hours to go through the course. So it's about like going through 2 popular science books, give or take. All right. So how does all of this work? Well, I mentioned interference, and you can see from this video here, which is taken also from our Understanding Quantum Computers MOOC, from one of the online tools for this, you can see the beating patterns and the interference in the waves here. Well, this is what happens inside a quantum computer. And the entanglement allows this to happen for an exponentially large number of possibilities and to create interference patterns across that large set of things. But keep in mind that this does not simply mean that we are computing everything in parallel. That's not that's a popular science kind of way of expressing how quantum computers work, that they execute on all the possible answers at the same time. And it's really not the right way to think about how quantum computers solve problems. Instead, what we need to think about is how to create those effective interference patterns among the set of possible answers. So what kinds of problems are we potentially able to work on? Well, in the upper right, you'll see there's a figure that says chess has 10 to the 120 possible positions in it. Right? But representing the state of a chessboard at any one moment is actually not too bad. So the amount of state space representation is actually pretty small, but we can't work on big data systems very effectively. So another sort of possible aspect of this that we think of as being particularly important is that we're looking for problems where there's an explosive or potentially exponential growth in the possible solution space. And we're looking for the sweet spot in structure. Now, as it happens, chess actually has maybe a little too much structure. There are already really excellent classical systems for doing this. And so it's not really directly a problem that's good to work on with quantum computers, but it gives you kind of an idea of the kinds of structure problems we're looking for. Now, we can consider problems that are potentially completely unstructured. We can consider problems that have a certain amount of hidden structure in them. And there's some special cases we can talk about. Now, before I show you the O of values for this, I want to point out that the constant factors really make a tremendous difference in this. And that's actually been one of the focuses of my own research over almost 20 years of working on quantum computing. So keep that in mind. For these unstructured problems, quantum computers can potentially take us from having to examine n possible solutions to only having to examine the square root of n possible solutions. Well, that's really not quite right, because what we're doing is creating those interference patterns, but we create the interference patterns in the order of square root of n iterations of our evaluation function. Now, the hidden structure, the most obvious one of these is Shor's factoring algorithm, which is very famous and was discussed briefly this morning. The best classical approach to this is this complex expression here on the right, known as the number field sieve. Many of you are probably very familiar with that. A quantum system can potentially reduce that using Shor's algorithm to a complexity of order of log cubed of n, where in this case, capital N is the actual size of this, and so the number or the magnitude of the number, and log of n would be the size of the number expressed in bits. And then in certain special cases like quantum chemistry, potentially we can gain a full exponential speed up going from order of n to order of log n kinds of computational levels in this. So what kinds of things can we possibly talk about here? Well, I just mentioned quantum chemistry. There are a number of aspects of quantum chemistry that are believed to lend themselves well to work on classical computers, although there's a lot of discussion among researchers right now on which ones can effectively be solved in practice on quantum computers. So it's very much an open area. But industrial processes like finding new formulations for agricultural fertilizer have the potential to bring us gains in the total amount of energy consumed worldwide, as well as other potential societal benefits. Battery chemistry is one problem that, in fact, some of the members of the Keio Quantum Computing Center have actually worked on. And in general, material science is a potential area. Now, quantum computers are often cited as being interesting for optimization problems. The challenge to that is that, number one, that optimization problems are often big data problems, and they come from areas like logistics problems, like scheduling shipping systems and things like that. And one of the biggest challenges for us here actually is competing with classical heuristics, which already generate very good answers as well. So another aspect of this, the environmental impact We can potentially substantially reduce the amount of energy that's consumed in data centers around the world if we can make computation more efficient. So is that going to actually happen? Well, Fugaco itself is on the order of 30 megawatts. And so the question is, how much computation can you do in a month for 30 megawatts? Data centers have been calculated to consume about 1% of the total world consumption of electricity. And so if we can have an impact on that area, then that has the potential to dramatically reduce the world's energy consumption and therefore have a positive impact even on issues like global warming. But a lot of that energy that's going into that computation is actually in quantum-friendly tasks like quantum chemistry, potentially training deep learning models, which you talked about in some of these optimization problems. Maybe some things like graph theory as well. So how much of this computation can we transfer from classical supercomputing systems to quantum systems? No one knows yet. Right? Anybody who tells you they know what the answer is, they're basing it on a tremendous number of assumptions, and some of those assumptions will probably prove to be true, and some of them will probably be prove to be false over the course of the next decades. So, this morning, in fact, we heard from Travis Humble about the work at ORNL, and he said that a good fraction of their overall workload is in fact quantum friendly. So I consider that to actually be a positive thing. All right, so this is somewhat of a reach in terms of human rights, but you can argue that secure communication is a human right. Some governments would disagree with that. And one way of doing that is blind quantum computation allows you to execute a program without actually sharing either your data or your computation with someone else. So let's say we have a quantum mainframe computer that we're sharing across the network. This is one of the first machines that was on the ARPANET in 1969 here, and that's the ARPANET itself. It was often accessed from a small mini computer that was at your local institution, so you connected via the ARPANET to this mainframe elsewhere. If we make all of these quantum, if we make your local access terminal quantum, the network quantum, and the mainframe quantum, then we can execute problems in a way in which the server learns nothing about either the client's data or the computation. And so you're actually executing this computation in a blind, secure fashion, but accessing supercomputing scale resources. All right, let me finish up real quickly here. A couple of areas where quantum technology and quantum learning is potentially advancing things include biology in the area of things like understanding photosynthesis, perhaps, and work on the LIGO, on the Gravitational Wave Observatory, which already uses a form of quantum state known as squeezed light. And so we're gaining benefits from the technology and from the learning there as well. So IBM divides the world, this time up into 3 eras: quantum ready, quantum advantage, and quantum business over the coming years. And I would say we are getting there. We are still at the toddler stage of life. Quantum computing walks and talks, but it can't really do much of anything useful yet. The biggest challenges are decoherence and scale. And we need to get good enough at the error correction so that the systems scale up to the point where we get to millions of qubits. We will get there. All right. Finally, there was a question this morning about building quantum computers. About 2 years ago, I collected a bunch of references and posted them on Twitter, and I collected that into a paper which is titled The Quantum Computer Architecture Tweetstorm. Please check that out if you're interested. And with that, I would say, please, let's all encourage our own students who will grow up to be quantum natives and will handle these problems for us. And with that, thank you for your attention.